Welcome to Lecture 2.3, Inhomogeneous Differential Equations and Affine Spaces. Here's the main idea. We've seen already how to solve, or at least some, linear homogeneous ODEs, and the set of solutions form a vector space. In this lecture, we'll look at linear inhomogeneous equations. Here's a definition for first order. Consider the following differential equation. Y prime plus a of ty equals g of t, where g of t is not equal to 0. So in other words, it's inhomogeneous. Define the related homogeneous equation to be the following. Basically, just take the original ODE and make g of t equal to 0. Now that's a different equation, so I should call it a different function, so I'm going to call it yh. So yh prime plus a of t yh equals 0. And let's suppose that its general solution is yh of t equals c1 y1 of t. So we know this is a one-dimensional vector space, the general solution that is. So any non-zero y1 of t that solves this ODE is going to be a basis for the solution space. Here's the main theorem, and it should be easy to see how it generalizes beyond just first order. The general solution to an inhomogeneous equation has the following form. Y of t equals yh of t plus yp of t, where yh of t solves the related homogeneous equation, and yp of t is any particular solution to the original inhomogeneous ODE. In other words, it has the following form. c1 y1 of t plus yp of t, where c1 is any real or complex number if we are going to allow those. Let's prove this. The word proof is a little bit strong. I really mean let's verify this. So saying that the general solution, this is a one parameter family of solutions, is equal to the homogeneous plus any particular solution, that's equivalent to saying if we take the general solution, this infinite family, and we subtract off any particular solution, then what we get solves the homogeneous ODE. So let's do that. So let's take y minus yp, and I claim that this solves the homogeneous ODE. In other words, yh prime plus a of t yh equals 0. So why is that? Or how are we going to check that? So to check that, we need to take the derivative and plug it in for yh. So the derivative of this, so let's see, so yh prime plus a of t yh equals, so yh prime is y minus yp prime plus a of t yh is y minus yp. Now let's rearrange things a little bit. I'm going to put the y's together, so this is y prime plus a of t y, and this is minus, let's see, yp prime plus a of t yp. And now look at this. This is a general solution, so if we plug this into the original ODE, we get g of t. So this thing here is g of t. And this is any particular solution, so if you plug this into the original ODE, you also get g of t. So this is g of t minus g of t equals 0. And that's all we had to check, that y of t, the general solution, if we subtract off any particular solution, we get a vector space of solutions. We get yh of t. This is the solution to the homogeneous ODE, which we know is a vector space. Now I want to show you some similar problems in different areas of mathematics that are a lot like this. First, parametrizing a line in Rn. Also, parametrizing a plane in Rn. Next, solving an underdetermined system of equations, ax equals b, So what I mean by this, by underdetermined, is that there are too many variables, so there will be infinitely many solutions. And then the last two, we're going to solve two differential equations that are inhomogeneous. The first one is a first order, and the second one is a second order. And I'll show you how the structure of the solutions for these two equations are going to remind you a lot of what's going on with these other three seemingly unrelated questions. Basically, behind the scenes, there are vector spaces, and these other structures that are like vector spaces shifted away from the origin by some particular vector or solution that we are going to call affine spaces. Let's get started. Let's remember how to parameterize a line in Rn. This is something that you should have seen in vector calculus. And I say Rn, this is going to assume that n is at least 2, although we can't really draw or visualize anything higher than R3, so we're just going to draw it in R3. So suppose that we want to write the equation for a line that contains a vector, v. So here's a vector v, and we want to describe the line that goes through that vector v, and that's through the origin. Now, if this were basic algebra, like you learn when you're 13 or 14, you learn about y equals mx plus b, and that works in the xy plane, but only in the xy plane. So obviously this is b, and this has slope m. So this doesn't work in R3 or R4. This just works in R2. Now in R3 you can write lines as intersections of planes, but this is a much simpler method that I'm going to show you, and it works in any number of dimensions. So this line, notice it contains the zero vector, that will be important, is just t times v, where t is any real number. So it's a set of all scalars times v. That is a vector space. Now, what if we want to write the equation for a line that's parallel to v, but not through the origin? How are we going to do that? Well, first of all, we need to find a vector on that line. Let's call it w, and claim any w will work. Here's one such w. So this new line, which does not contain the zero vector, is the old line tv plus this w. In other words, it's what we get if we just add w to this line and we shift it up. We just shift it up from going through the origin, going through w. And algebraically, that's the set t times v plus w, where t is any real number. And notice that any particular w on this line will work. If we had used a different w, so call it w prime, if we had used this one, w prime, we could have done, oops, these are all supposed to be parallel. These are done the same thing. And in that case, we would get that this set is equal to tv plus w prime, where t is a real number. Now, with a different parameterization, different t's are going to give us different vectors, but as a set, these describe the same line. Now, they are not vector spaces. They are vector spaces shifted away from the origin by any particular vector on that space, either w or w prime or something else. This is what we will define this soon. These are what affine spaces are. They are almost vector spaces. They are spaces or sets I should say, that if you subtract a single vector from, you get a vector space. More on this shortly. Actually, before we go on, I want to do this in one higher dimensions. Not in a higher Rn, but I want to go from a line to a plane. So let's draw this pretty quickly. I don't have a new slide for this. I just want to compare it to what we have here. So here's x, here's y, and here's z. And now let's suppose that we have two vectors. So here's, oops, it's supposed to go through the origin. So here's v. Now I'm going to call it v1, and here's v2. Now these things determine a plane, right? Determine this plane. They are a basis for that plane. So if we want to parameterize that plane, I'm going to call this plane P, and we do that by P is the set of SV1 plus TV2, where S and T are real numbers. So they range over all the set of real numbers. So now what if we want to write the equation for a plane that is parallel to this. So suppose it's up here. Well, what we do is we take any vector on that plane. Let me call that W, and then that new plane is P plus W. So P plus W is SV1 plus T V2 plus W, where S and T are any real numbers. And any W here is going to do the trick. So notice once we're up here, so W plus V1 is there, W plus V2 is down there, and we get that new plane. Now, this plane not through the origin and this line not through the origin, these are not vector spaces. They do not contain the zero vector, or the origin. But they have the property that if we subtract anything from them, for example, like this W, then it brings them down to the origin and we get a vector space. We'll define this formally fairly soon. Basically, that's how we'll do it. We'll call these things affine spaces. But first, I want to compare how this relates to a few other areas of mathematics that you've already seen. Next is a classic problem in linear algebra, not the vector space theoretical stuff I've been showing you, but any intro undergraduate linear algebra course, you will learn about how to solve an underdetermined system of equations, AX equals B. So this means that we have a system of equations that has, in quotes, too many variables. So there are infinitely many solutions. Here's an example. Two equations, 2x plus y plus 3z equals 4, and 3x minus 5y minus 2z equals 6. Now, it's convenient to write this in matrix form, or AX equals B form, and if we do that, we get a 2 by 3 matrix times a 3 by 1 vector equals 4, 6. And that matrix is 2, 1, 3, 3, negative 5, negative 2, times the column vector x, y, z equals 4, 6. Let's recall how to solve this thing. So you first solve the related homogeneous equation. So basically you take this AX equals B equation and you set the B equal to 0. So just instead of 4, 6, put 0, 0 in here and solve that first. So AX equals 0, technically you're finding the kernel of A, or the null space. You're looking for all vectors x such that A times x equals 0. That's what the kernel or null space is. Second step, find any particular solution to the original equation AX equals B. Let's call that XP. Now, how would you do this? Well, this is something I'm sure you can figure out. Let's look at the original equation, and you know there's free variables, or there's more things than you need. So let's just get rid of one of the variables. Let's set z to be 0. So if we set z to be 0, then we get 2x plus y equals 4, and 3x minus 5y equals 6. And this is something that we can solve by hand. So it's not hard to find any particular solution. Now we didn't have to set z to be 0. We could have set it equal to be 1, or we could have set x to be 0. Once in a while we get unlucky and we can't solve this, but generally this is going to work. Once you have these two things, both the null space or the kernel and any particular solution, then you just add them together and you get the general solution, the set of all possible solutions. X is just the kernel of A plus XP. And what I mean by this is it is an infinite set consisting of, I'm going to call it x naught plus xp, where x naught is in the kernel of A. Does that look familiar? Again, xp is fixed, and this is an infinite set, so we get something like this. This works because geometrically the solution space is just a line or a plane, etc., that's not through the origin. So it's just like what I was showing you before. So here's this example above. Let's actually solve this. So here are two possible ways to write the solution. So the first one, x equals c times 1, 1, negative 1 plus 2, 0, 0. Now, obviously I didn't do this step by step, but just notice that 1, 1, negative 1 solves this equation. And Now, you can try that by plugging that in for x, y, and z respectively, or if you recall some of your how to do matrix multiplication, there's a nice little trick for this, that saying that 1, 1, negative 1, actually let me write it up here. So 1, 1, negative 1 is in the null space, which means ax equals 0. So that means that 2, 1, 3, 3, negative 5, negative 2 times 1, 1, negative 1 equals 0, 0. And one way to check that is recall that if you multiply a matrix times a vector like this, what you're really doing is you're multiplying that first entry 1 times the first column plus 1 times the second column plus 1 or plus negative 1 times that third column. Oops, I meant to write that out. And it's easy to check that 1 of the first column plus 1 of the second column plus negative 1 of the third column equals the 0 vector. So yes, this is in the null space, and the null space, being one-dimensional, is just all scalar multiples of that. So notice that here is one possible way to write the solution. It's easy to see that 2, 0, 0 is a solution as well. But that's not the only way to write it. So here's another way. I could have written the particular solution as 10, 8, negative 8. And now how did I get that? Well, really what I just did is I took the null space, c times 1, 1, negative 1, and I plugged in c equals 8. If I did that, I got 8, 8, negative 8, and I added that to 2, 0, 0 to get this one. So I can add to my heart's content anything from the null space to a particular solution, and I get another particular solution. So these are two different ways. Think of this as a W and this as a W prime. Two different ways to write the solution. Our next example takes us back to the world of inhomogeneous differential equations. So here's a simple first order equation, y prime plus 4y equals 8. Now how would you solve this? Well, most people in their Intro ODEs course learn that you can separate variables, in this case, because there's no t floating around. Or you might want to use the integrating factor method or variation of parameters. So there's three distinct ways to do it. I'm going to show you a different way. This is a way that you likely haven't seen before, although you've definitely seen it for second order equations. Step 1. Solve the related homogeneous equation. Take this 8, make it 0, and solve that equation. And this is something that you should be able to do by inspection. It is c e to the negative 4t. Step 2. Find any particular solution, yp of t, to the inhomogeneous ODE. Now, how are we going to do that? Well, this is a constant on the right-hand side, so it should give you a hint that there might be a constant solution. Now, how would you find a constant solution? Well, if yp of t is a constant a, then its derivative is going to be 0. So we just set the derivative equal to 0 and see, can we solve for y? And look at that. Lo and behold, y equals 2 is a solution. So by inspection, we can see that 2 works for a particular solution. So step 3, we just add these things together to get the general solution. Y of t is the homogeneous solution, yh of t, plus yp of t, any particular solution, and we get c e to the negative 4t plus 2. So while this general solution above is unique, this is an infinite set of functions, the presentation, the way we write it, need not be. It's just like how we could have used a w or a w prime for those equations for lines and planes a couple slides ago. For example, I could write it this way. I could say y of t equals c e to the negative 4t, and then here's a different particular solution, plus 5 e to the negative 4t plus 2. Where did I get this 5? Well, I just took my general solution and I plugged in c equals 5, and that is a solution. So I used that as my particular solution instead of this Very simple one. Now obviously it's probably simpler if we just use the plain old 2, but I did this so I could show you that either of these is going to give us a formula for the general solution. Next example. It's almost the same thing, but now it is a second order ODE. So we'll solve it the same way. Step 1. Solve the related homogeneous equation. YH double prime plus 4y equals YH equals 0. So now this is a little bit harder. When you see this, you should be thinking sines and cosines. And indeed, the solution is YH of t is C1 cosine of 2t plus C2 sine of 2t. Step 2. Find any particular solution, YP, to the original ODE. Now the same one's going to work because there is a constant solution. We can get that by setting y double prime to be 0 and y once again is equal to 2. So by inspection we can take our particular solution to be equal to 2. And step 3, we add these together to get the general solution. Y of t equals C1 cosine of 2t plus C2 sine of 2t, that's the homogeneous solution, plus 2. And once again, while the general solution above is unique, this particular presentation need not be. For example, we could write it the following way. We could, instead of using 2 as our particular solution, we could take something else in here. We could take, let's take C1 to be equal to 5 and C2 to be equal to -3. And now we have a new presentation of our general solution. Now that you've seen some examples, I will, as promised, go back to the topic of affine spaces, something that I want to define formally. So the solutions to linear homogeneous ODEs, as we've seen, form a vector space. For a first order ODE, that's a one-dimensional space. So a basis is just any non-zero function. So the general solution is C1, Y1 of t, where C1 is any real number or complex number, depending on what number system you want to work over. For a second order equation, the general solution is two-dimensional. It's a two-dimensional vector space with basis y1 and y2 for any solutions that are not scalar multiples of each other. So we get something like C1y1 plus C2y2, where C1 and C2 can range over the set of real numbers or complex numbers if we choose to work in that domain. In contrast, the solutions to linear inhomogeneous ODEs have the following form: C1y1 of t plus a particular solution, or C1y1 plus C2y2 plus a particular solution. Again, for C1 and C2 are any real or complex numbers. These, as we've said, are not vector spaces, but they are very close to being so. They are called affine spaces. Intuitively, an affine space looks like a line, a plane, or a hyperplane, etc., but not through the origin. Here's a formal definition. An affine space is, well, before we go, let's remember what a vector space is. It was a collection or a set of vectors V and a set of scalars F, where the scalars, we call them F because they were a field, an algebraic set where we can add, subtract, divide, and multiply. So now an affine space is a set A of vectors, very similar, and a set of F of scalars, but here's what we want, such that for some particular vector, W, the following set, A minus W, meaning the set of all vectors in A, subtract minus W, that is a vector space over F. So basically, all an affine space is it's a vector space shifted away from the origin by some V. Now in my definition I say it's an affine space if there is some particular vector in A, and it turns out, not hard to see, that any vector in A will do the trick. Let's go back to our example of a line. So let's take any non-zero vector, V, and the line, let's call it L, containing it is a vector space. It's the set of all scalars t times v, where t is any real number. And here we really should talk about real numbers because we are living in R3. At least I've drawn it that way. Now, any parallel line A that's not through the origin is an affine space. So hopefully that you should be able to see that geometrically. Here's why it's true algebraically. Recall that an equation for this line, A, is just TV plus W, or the set of all T times V plus W, where T is a real number. And W can be any particular W on the line will work. This line satisfies the definition of an affine space, because if we take this line and we subtract W from it, we get a vector space. So A minus W, algebraically, is the set of all TV plus W, that's what A is, minus W, where T is any real number. And of course the W's will cancel, and we get the set of all TV where T is a real number, which was our original line, which is a vector space. Now you may be wondering, well, I conveniently used the same W here and the same W here, but it didn't matter. So they canceled here, and if I used a W prime, they wouldn't, but we would still get the same line. I mean, think about taking this line here, shifting it up by W. Let's do that here. And then let's shift it down by some W prime. These are supposed to be parallel and the negative of things on the line. And if we do that, we will get back to the original line. Equivalently, instead of writing TV plus W right here, I could have written TV plus some W prime. Still the same line, doesn't change everything as a set, but now if I subtract W, subtracting W from the line, the affine line, A, still gets me the vector space L. Now I want to do a similar example, but with ODEs. I'm leaving the picture in here to give you the hint of the same geometric structure. So now suppose we have a non-zero function y1 that solves a homogeneous equation, yh prime plus a of t yh equals 0. The solution space to this homogeneous equation is a vector space. It's a set of all functions of the form c1 y1 of t. Now, suppose that yp of t is a function that solves an inhomogeneous equation that has this as the homogeneous part. So y prime plus a of ty equals g of t, where g is not identically 0. The set of solutions to this inhomogeneous equation, let's call it A, is a set of all functions of the form c1 y1 plus yp. This is clearly not a vector space. It does not contain the origin. But it is an affine space, because if you take the set A and you subtract yp from it, we did this a few slides ago, you get, this is the general solution to the inhomogeneous equation. You subtract off yp, then the yp's cancel, and you get the set of all c1 y1, which is the original line or subspace L, the original set of solutions to the inhomogeneous equation, and that is a vector space. So there's really no difference between these linear ODEs and these lines and planes. It's just what we're calling them. Here we're calling them V and W, and down here we're calling them Y1 and YP. I want to conclude with an important remark about changing variables. This is something that you've done in many situations, probably without even realizing what was going on behind the scenes. So when we do a change of variables, for example, maybe in R2, we're going to let U1 and U2 be x1 minus a and x2 minus b. Or maybe when solving an ODE, you want to let U of t be y of t minus yp of t. In both cases, all we're doing is making an inhomogeneous equation into a homogeneous one. I'll do an example in both cases. In the first case, suppose we have R2, so x1 and x2, and let's take a vector, let's call it a, b. So when we change variables, we're letting u1 equal x1 minus a, and u2 equals x2 minus b. So notice that u1 is going to equal 0 if and only if x1 equals a, and u2 is 0 if and only if x2 equals b. So what we're doing, in essence, is we are defining a new coordinate system. Instead of x1 and x2, we're using u1 and u2. And u1 is 0 when x1 is a, so along this horizontal line. So this is where u1 is 0, and then u2 is 0 when x2 equals b. So that's along this, I call that a horizontal line, right? That's a vertical line. Along this vertical line, horizontal line, oh gosh. So this is u1 and this is u2. So we are moving the origin, we're moving our axes, so our desired point, A, B, is now the origin. Okay, so what? So let's suppose we have a vector space. Now, a line. Let's take, say this is V1, and let's take a line through, I could have just called that V. So this is T V1, right? Now a line parallel to that goes through AB is just T V1 plus W, and let me call this W. So this line is an affine space. It does not go through the origin. However, when we change variables, well, it does not go through the origin in the x1, x2 plane. But when we change variables, when we let u1 and u2 be these guys, now we are redefining our coordinate system so this affine plane, affine line goes through the origin. So we're defining our axes so this affine space is now a vector space. We're making an inhomogeneous equation, TV plus W, into a homogeneous one. Now let's do the same thing for differential equations. Here's an example that should be familiar from your Intro ODEs course. This is Newton's law of cooling. So let's suppose that the rate of change of the temperature of a cup of coffee is proportional to the difference between the coffee temperature and the ambient temperature. Mathematically, this says that if y of t is the temperature, then y prime, so is proportional to, that means times the constant, we're going to put a k in front because it's a decay equation, times this difference, which is y of t, the temperature, minus the ambient temperature, let's call it 72. Okay, so if you were to solve this in your Intro ODEs course, you probably learned several methods. You could separate variables, you could do the integrating factor method, or you could use variation of parameters. Well, I'm going to show you another method that I've touched upon today, and you'll see it more in the next lecture, which is called undetermined coefficients. It's basically solving the homogeneous equation first and then finding a particular solution. So this is, if I multiply this out, this is negative ky plus 72k. So the related homogeneous equation is yh prime equals negative ky yh, and the solution to that, obviously, this is exponential function, so this is c e to the negative kt. Now, for a particular solution, you first ask, is there a constant solution? Well, if there is, then y prime is equal to 0, so we set this guy here equal to 0. So let's set that equal to 0 and solve for y, and you clearly see that y, let's call it yp of t, is 72. It's actually probably easier to see just from this equation, that if the left-hand side is 0, well, k can't be 0, so then y has to be 72. So now we have our solution, which is y of t equals c e to the minus kt plus 72. Okay, so what does this have to do with changing variables? Well, if I were to graph this solution, where should I fit this? Let me put this right here. So this is 0, this is t, and this is the temperature y of t, and this is 72. That's supposed to be a flat line. I think you can imagine this flat. Well then, the solutions are going to look like equations that decay to this line. Let's make a change of variables. So this 72, this is Fahrenheit, which is an arbitrary temperature system anyways, but even Celsius is not perfect. Let's change variables. Let's declare room temperature to be 0. So things aren't decaying to 72, but they're decaying to 0. That's more natural. In that case, 0 is going to be a steady state solution. Here, 72 is a steady state solution. So I'm going to let u of t, or u equals y of t minus 72. Let me drop the of t's pretty quickly. So u prime equals y prime. So now let's plug this back into here. Let's express this equation in terms of u instead of in terms of y. And think of u as the temperature, not in Fahrenheit, but with respect to 0, or with respect to room temperature. So if u is 10 degrees, that means 10 degrees above room temperature. And if it's negative 10, it's 10 below. So let's plug this back in. So y prime equals negative k y minus 72 becomes u prime equals minus k times u. Now look at this. We've made our equation homogeneous. So u of t is clearly c e to the minus kt. So all we've done is up here in this graph, we have declared that instead of here this was y equals 72, I'm going to instead declare that that is u equals 0. So the origin is moving up here, and now these, I don't need to redraw them, the solutions are decaying to 0 instead of decaying to 72. So again, all we are doing is making an inhomogeneous equation right here, make it into a homogeneous one. And we do that by changing variables, by redefining where the origin is. And we'll see this a lot more when we study partial differential equations in a few sections. So stay with us.